Basically a mix of color finders here. We don't know that they're still the right kind of targets because the actually still sneak in.
Okay, so welcome everyone. We have a very crowded room, and Julian, I guess it's because of you. We should invite you every week. We just heard an exceptionally high signal to noise ITC colloquium by Gil Holder. Where is Gil? Here. Over there, and we'll hear more from him in a few minutes. Before we start, I wanted to acknowledge the presence of 13 prospective graduate students. Please raise your hand so we know who you are. And we very much hope that all of you will join us, although I don't know if we have enough office space, but we will be happy to have all of you, and it's really a great pleasure to have you here. And I just wanted to add that we're not trying to impress you. This is what we have every week. We don't put any makeup. We ask questions the way we usually do. So if you are impressed, come. So we'll hear from Julian Munoz, who is here at the CFA and already accepted the faculty position in Austin. I hear that Austin is even better than New York City these days. They have everything.
If you, yeah, by real estate prices, yes.
Also, you really improve the science, I guess, but also in terms of culture, it's really quite fantastic. So we will hear from Julian about an analytic model for the first galaxies and the 21 centimeter signal, and then we'll hear from Emma Chickles from MIT, not very far from here. Where is Emma? Over there. She will talk about searching for eclipsing white dwarf binaries in TESS 200-second observations. Then we'll hear from David Bushnov. Did I say it right, David? Where is David?
Doesn't matter.
He's at the ITC, and he will talk about cluster assembly and the origin of mass segregation in the Starforge simulations. And finally, we'll hear from Gil Holder, who I regarded as a theorist until I heard him this morning. It sounds like he's slowly drifting in the direction of being an observer, but perhaps that's a sign of maturity as you age. And he will talk about the topology of large-scale structure as traced by galaxies and dark matter halos. Julian.
Thank you. Yeah, so I know most of you, except maybe 13 of you. But for the rest, if you don't know me, I'm Julian. I've been a postdoc here for the last few years. I'm moving to UT Austin as a faculty. And I'll tell you about this title that I'm going to summarize as a short talk, as a punchline, which is I develop an effective model to analytically, this is the key part, calculate nonlinear correlations at cosmic dawn, and this will enable direct inference from 21 centimeter data. It's a lot of words, but I'm going to give you the context of why I care about this and why you should care about this. I'm going to show a picture, cosmic evolution of the universe since the epoch of the CMB, redshift 1000, cosmic dawn, first galaxies form, reionization to today. But of course, we haven't mapped all of this. This is roughly what we've mapped. As you start getting towards earlier times, our knowledge gets fuzzier and fuzzier. We've been able to sort of peer into cosmic dawn by using data from Hubble and recently from James Webb. This really given us a lot of information, but the data these telescopes can see, the galaxies they can see, are really just the tip of the iceberg. These are the brightest galaxies at cosmic dawn, in fact, maybe too bright, according to James Webb. But if you wanted to know the rest of the iceberg, you want to know the average citizen of cosmic dawn, this is very difficult to do directly, observing them. A way to go around this is to measure their effect on the intergalactic medium at all through the 21 centimeter line, which is what I'll talk about, and how it's difficult to model, and why we have to develop these sort of like intuitive analytic methods. So the very, very short idea is that the CMB emits a ton of photons, and Gil told us a lot about the science you can do with them. Something else you can do is look for the ones that are absorbed by hydrogen on the way. If they have a wavelength of 21 centimeter, at some point, they can get resonantly absorbed by neutral hydrogen. And how many I'm missing, we parameterize to this 21 centimeter brightness temperature, T21. So this is the equation. The first factor, T0, is just some constant, depends on cosmology, fairly irrelevant. But the other three are where the meat is. So the first one, the densities, tracks the large-scale structure. So I have more density, it's more likely to absorb something. So I can measure, I can map that large-scale structure with that. The second is the neutral fraction, the epoch of reionization. So it tracks how much neutral hydrogen there is. Ionized hydrogen doesn't do any hyperfine. And if we only had those two, we'd be in good shape, because we have a whole sort of range of observables and models from analytic methods, like some developed here by Lars and collaborators 20 years ago, to hydro simulations with sort of details that you can use to compare against the data. So if we only had those two, it would be fine. So I'm going to talk about the third one, obviously. The third one tracks the spin temperature, so the thermal state of the hydrogen at different points. And this term is tricky, depends on the star formation rate density, or SFRD, and is non-local and nonlinear. It's non-local because you have to integrate over all the different distances away from a point, because stars will emit photons, this will travel, so it's non-local in space. If this was the only hurdle, however, Avi and Renan, that was about 20 years ago, developed a method to go around these non-localities. So if it was linear but non-local, it would still be fine. But it's also non-linear. And that's because the star formation rate density itself is a non-linear function of the density field. So I cannot do what I do for the CMB, where I have initial conditions, and I somehow 1D map them to like a final result that I can compare with data. So what we've done since about 2010 is rely on simulations that range from realistic to unrealistic, semi-numerical, and just try to compare that with data. But this still takes hours to run, because you need to do this in a whole grid, you need to put it on the grid, you need to evolve the things. So this, again, is because the star formation rate density is nonlinear. You may wonder, how nonlinear is it really? Very, extremely nonlinear. At cosmic dawn, this star formation rate density divided by a value of 0, so this is how it fluctuates against density. and I've picked the value of redshift and radius to give you some cosmic dawn reasonable values. This is almost an exponential. And the reason is, if you're cosmologically inclined, is because there's an integral over the halo mass function with some astrophysics inside, and the halo mass function varies exponentially. So at cosmic dawn, halos are exponentially rare. If I change the densities a little bit, how many halos I get, it varies exponentially. And in fact, you can actually do an exponential fit, and it works really well. The regions where it kind of like starts to break down towards the edges are regions that are where the density is not populated. There's a PDF here. So this exponential thing seems to work pretty well. Again, to give you more a pictorial idea, here's given a density field, what the star formation rate density would be in a particular model. Here's what the exponential approximation would be. By eye, pretty good. And now you might wonder, well, this is cute. It's a cute mathematical trick. Why do I care? And the answer is that if this is true, and again, seems to hold up, the 21 centimeter signal is a sum of exponentials of the density with some coefficients. Not going to get into all the details. But the density is a Gaussian. So e to the something Gaussian is a log normal variable. And there's something for which I have full analytic knowledge of all correlation functions to all orders. So from the power spectrum of density, delta square, I can get the power spectrum of 21. I can get any correlation function I want with all these nonlinearities included. Again, if you're cosmologically inclined, you can think of correlation functions and how the correlation function of a log normal depends on the correlation function of a Gaussian. But OK, this is how you go about correlation functions. So what I've done is I wrote a package called Zeus21, which is on GitHub, which does this whole process. It goes from densities, gets all this star formation rate density on different radii that you will integrate over, and they're approximately exponentials. From these, you get fluxes, and from the fluxes, you get the signal. And it does so in about a few seconds. And what I decided to do is something risky, is I'm going to do a live demo of this. So someone did this a few weeks in this lunch, and I really enjoyed it. So let's see how it goes. So the code, again, it's called Zeus. Let's import it. It works. So it reads cosmology from class. So class is the standard Boltzmann solver that we know and love. And the first thing it's going to do is run class, which is actually going to take the longest of anything I'm going to show you here. Because even though class is very fast, it still needs to solve to very high K. So this is going to be the bottleneck here. So it's going to take about 10 seconds wall time, 40 seconds is multi-threaded. But from now on is what my code will do, will actually do the astrophysics. So it's going to find the global signal, it's going to find the fluctuations, it's going to store them. And you see it takes about 5 seconds in a single core. And now you can plot everything. You can plot the global signal. You can see here. High redshift, there's nothing. First galaxies form, it goes down. X-ray heating brings it up. And then you'll get reionization later on. You can plot the temperatures. So again, temperature of CMB in red. It just decreases with redshift. Kinetic temperature is low, gets heated by X-rays. Spin temperature in black. When the first galaxies form, goes down. And here, sort of like the money plot is the power spectrum versus wave number. Black is the full nonlinear signal. This is what you will get with a linear approximation, so it's off. You need to, this exponential, you need to include it. Having a bias expansion wouldn't do this for you. And of course, this is a particular set of parameters. You can run a different one with a lower X-ray luminosity, for example. I'm going to show you again. If you only run the astrophysics, this takes a few seconds to run because the cosmology is fixed. And you can plot it. If you lower the X-ray luminosity, the signal is deeper. So you get colder gas, so more absorption. The power spectrum is larger. It's easier to detect. So this tutorial, one like this, is in the GitHub. So you can just go, play with it, download it. But I wanted to show you, just this is on the GitHub. You could get a power spectrum in your computer in like 10 seconds. So again, all this is very cute. But you may say, this is still all a theorist's vision. It's analytic things. How does it compare with simulation? So here, the gold standard of inference in 21 centimeters, 21 cm fast. So I could plug the same model and try to see compare with them. This is what the global signal looks like in one versus the other. They're very much on top of each other, like a few percent. But this is easy, right? This is the average across the universe. So like things will average out. But this is where the true test is going to be in the fluctuations. You could have guessed they were going to be OK. Otherwise, I wouldn't be giving this talk. So the black is my code. The red is 21 cm fast. They agree to like tenths of percent. And that is as much as I trust semi-numerical simulations to begin with. These are not hydro. These don't have ray tracing. These rely on approximations to begin with. But rather than analytically compute things, they put things on a grid and get the power spectrum of that. So yeah, but like the black line takes seconds, the red line takes hours. So what's next? The first obvious thing is we can do inference with this. This takes a second to run. This is faster than class. So you can do inference on the CMB. You can do inference on 21 centimeter. We have increasingly better limits on the 21 centimeter power spectrum. They're getting deeper and deeper. And the black line is sort of like our best guess model. But we can vary the parameters. We can vary the X-ray luminosity and start putting the line up until we collide with these limits. Another thing you can do if you're dark matter inclined like I am is like to look for models of dark matter that heat or cool the gas. In particular, because of edges, it's a terrible screenshot, I apologize. Because of edges, we want to rule out models that cool the gas at cosmic dawn. These models will give you much, much more power, which is easier to look for with Hera, but you need to plug with the CMB. You need to do the whole cosmic evolution, which this code can do because it talks to class. Moving at the future, we want to, again, measure the whole iceberg. We want to find the average citizen of cosmic dawn. So we want to look for things like POP3 stars. And this is something that requires a little bit of thinking to put in this formalism, because you have density-dependent feedback because of Lyman-Werner. But there's something that is interesting to develop. And the final thing is that in principle, you can do imaging. You have a field that is a sum of log normals. It's a well-known statistical field. So you could populate 3D boxes with it, do imaging, subtract foregrounds, you name it. So if you're interested in any of this, developing the code, going to GitHub, anything, I'm here for a few more months. Talk to me. But otherwise, I'll take any questions. Thank you.
Julian, the question is, you assume that the density fluctuations are Gaussian, of course. That's the source of the exponential dependence. And could you reverse the argument and constrain Gaussianity from future data, comparing that to your calculation?
Yeah, it's a very good question. I haven't thought about it too much, but so basically what you're saying is here, I'm assuming, yeah, this is going to be some deltas Gaussian. People have worked out what the halo mass function, how it varies when delta is not Gaussian, because you change the tails. I haven't thought of putting that here. We thought of putting this in the luminosity functions of Hubble. So we constrain FNL from Hubble data. But we haven't looked at, I personally haven't looked at doing this in 21
Maybe it will change significantly.
I think it might.
Yeah.
I think Planck has very tight constraints, so it's hard to do better than Planck. But it's different scales.
What is the current constraint? F of all the
5.
5?
For local types, about 5.
5, okay. Any other questions to Julian? Well, go ahead, please.
You said you do not believe the numerical solution will be like 10%.
Yeah.
But what, like RG simulations, are those more believable, and if so, could you compare? I mean,
Yeah, so that's a good question. I think people have done detailed comparisons for the whole, like the first two field, like density and the reionization part. People have done more detailed comparisons. When it comes to adding X-rays, Lyman alpha, I don't know of a detailed comparison between semi-numerics and like ray tracing with Hydra. And that's why I don't trust it any more than 10 sub%. Which is good enough for the inference we want to do, by the way. Like, the Hera data right now is 100% error bars. Even when you get a text, it will be 20, 30% error bars. But yeah, for next generation, I think we need a whole continuum of approaches from very detailed, very expensive to this sort of like very cheap, and to need to be able to see how they match to each other. Like they need to agree. Yeah, that's a good question.
So Julian, for I guess the older people in the audience, how much longer do we have to wait until the signal will be detected?
If only it was up to me. So, I mean, I kind of removed the dates from this plot, but like these limits up here, the blue ones are like 2014 or so. The 2022 Hera's here, 2023, hopefully 2023. Data we're collecting now, analyzed soon. The sensitivity will be down to like roughly where the theory is, assuming there's no hiccups. And that's where my experimental colleagues have to really go fight the hiccups and fight the foregrounds and these things.
Is it really Hera or LOFAR? Who will it?
I think it's going to be Hera, because the design of the array was designed for this.
Okay.
LOFAR has the stations far away, so you have better angular resolution, but you lose sensitivity on the large scales, which is where the cosmology lives. So I think it's going to be Hera, and I think it's on the scale of 3 to 5 years. Being pessimistic, it could be next year. Maybe
Well, for you it's important because the question is whether it's before you get tenure or
Thank you.
I promised it worked like 20 minutes ago. Yeah. Yep, okay. Okay, awesome. Okay, hi everyone. My name is Emma Chickles and I am a second-year grad student at MIT. I've been working with Kevin Burge, who is a Pappalardo Fellow, also at MIT. We've been thinking about TESS Cycle 5, which began back in September 2022, and was when TESS's full-frame images was reduced from 600 seconds to just 200 seconds. And I'll be talking about how this is really exciting for white dwarf astrophysics. To give a very quick overview of what I'll be talking about, first, I hope to convince you that white dwarfs aren't too faint for TESS and is able to detect eclipses from short-period eclipsing white dwarf binaries. Then I'll talk about how the 200-second observations have a fine enough sampling to detect the narrow eclipses of double white dwarf systems, which I picture on the right. And then lastly, I'll talk about how we hope to use the 200-second observations to identify cataclysmic variables and help better understand the orbital period distribution for CVs. So with that, let's get into it. So TESS, for those who aren't so familiar with it, was launched in 2018, and it is an all-sky optical survey that with the goal of detecting transiting exoplanet around nearby and bright stars. And in year 5 of the TESS mission, the exposure time for these full-frame images, which are these large 24 by 96 degree strips, was reduced from 10 minutes down to 200 seconds. Now, this doesn't matter too much for detecting exoplanets since transit durations are already measured on the order of hours, but this is really exciting for short timescale stellar variability. And with the compact nature of white dwarfs, we have lots of minute scale variability, such as pulsations or minute-long eclipses from double white dwarfs, for example. So as part of our Cycle 5 proposal, we are looking at 1.4 million Gaia EDR3 white dwarfs and extracting light curves and searching for periodic signals, for which we're using the Box-Least squares algorithm. Well, most of our intuition for the limiting magnitude for TESS comes from trying to detect short amplitude transits of exoplanets around main sequence stars. But I hope with this slide to convince you that TESS is also capable of detecting signals from faint objects. So let's take a look at this 49.7 minute known fully eclipsing AMCVN. It was actually pre-selected by TESS to observe with a short 20-second cadence, which is what we see on the far left. It has a peak apparent magnitude of just 19 in Pan-STARRS I band. In this figure, we've binned the 20-second light curve into different exposure times with the corresponding Box-Least squares power spectra on top and the phase-folded and binned light curves on the bottom. Even if you're unfamiliar with Box-Least squares, we're calling like a presence of a signal to be a peak in the power spectra corresponding to the orbital period. So if we look at the 30-minute cadence panel, there isn't an apparent signal, but as we go to the 10-minute cadence, we start to see the peak from the orbital period, but there's also competing peaks of comparable strengths. it's not until we get down to the 200-second cadence that we see that clear peak from this object. So this is a direct demonstration that with the 200-second cadence full-frame images, we can get to these apparent magnitudes for some sources, thanks to high amplitude variability and short orbital periods, meaning that there's many eclipses to catch over the month that TESS observes. So high amplitude variability, short orbital periods, that's the case with binaries with white dwarfs. To give an overview of how we do this systematic search, we start with the raw full-frame images and extract our own light curves with aperture photometry. This is very fast, which we need for our purposes, searching a lot of sources, but struggles with crowded fields such as in the galactic plane. If you're interested, I'd have to take questions later. And then we do a period search with the Box least squares algorithm and visually inspect the highest significance candidates for an obvious signal. For those, we cross-match with other large catalogs like Assassin, Atlas, and ZTF to see if the signal we see in the TESS light curves is also present in those surveys' light curves. So as practice for the 200-second cadence data, we ran a period search for Sector 41, which observed 35,000 white dwarfs at a 10-minute cadence. And by looking at the highest significance candidates, we indeed recovered that 19th magnitude AMCVN from the previous slide. And this was with 10-minute cadence, and now moving to 200-second cadence, our sensitivity is only increasing. I also want to mention that all of the light curves we extract and the Box least squares power spectra and Lumsgargle periodograms will all be made publicly available as part of our Cycle 5 proposal. So if you're interested in other minute scale variability in white dwarfs, such as from pulsations or rapidly rotating magnetic white dwarfs, then this could be a cool data set to look into. Okay, with my last few minutes, I am going to talk about or introduce two science applications that we're focusing on for our period search. The first being how TESS is a unique opportunity to catch those eclipsing double white dwarf binaries. These are interesting systems since they're possible progenitors of type 1a supernovae, which are of course important, for example, for measuring cosmological distances. But we have not yet found a double white dwarf system that fits our double degenerate model, which would involve the merging of two carbon-oxygen white dwarfs. And now finding an eclipsing helium white dwarf is difficult enough, but a carbon-oxygen white dwarf is even more massive and dense. So existing ground-based surveys like ZTF or upcoming LSST might not have enough dense sampling to catch the very narrow duty cycles of these double carbon-oxygen white dwarfs. But with TESS's new 200-second cadence, with over 10,000 photometric samples in a continuous month, the sampling might just be fine enough to possibly find a system like this. Also, our goal is to find eclipsing double white dwarfs, so eclipses will help yield precise constraints on the masses and radii of the objects, which will allow for tests of the equation of state for these white dwarfs. And by identifying these systems now, then over the next few years, we can monitor these systems for orbital decay by gravitational radiation. Speaking of gravitational radiation, LISA will be launched in the 2030s and will operate in the low frequency regime, 0.1 millihertz to 100 millihertz, as compared to LIGO's frequency of 10 hertz to 1,000 hertz, I believe. So if we think about this empirical relation, which applies to binaries with a mass ratio of less than 100, and plug in the density for a typical white dwarf, we see that the orbital period for these white dwarf binaries is right at LISA's sensitivity. As compared if you plugged in the density of a main sequence star, it can't fit into these tight orbits. So it's going to be these binaries with a white dwarf that will be the most numerous and persistent sources of gravitational waves in our galaxy and detectable by LISA. Coming online next week, we'll soon have 24 A100 GPUs, which will make our search much more powerful. We'll be able to search a larger frequency grid and finer eclipse duration grid, and hopefully we might find a couple of these in test data. We will see. Lastly, I want to touch on how we are using our period search to identify eclipsing cataclysmic variables. So one of the most striking features about the cataclysmic variable period distribution is this observed period gap from 2 to 3 hours. And the accepted explanation for the past few decades of why this exists has been disrupted magnetic braking. We expect that CVs with orbital periods larger than 3 hours have orbital evolution dominated by magnetic braking, which stops when we hit 3 hours and the donor star hits the mass of a convective M dwarf. That decrease in angular momentum loss would suppress accretion, and since CVs are usually identified via UV or X-ray emission from heated accreting material, then this is an explanation for why we see this observed period gap. We instead want to observe this period distribution via eclipses, so we'll be unbiased to those selection effects from identifying CVs via accretion signatures. So our work so far. Right now we've performed our period search for sector 61. I wanted to highlight a few recovered binaries that we found so far, such as the 17th magnitude cataclysmic variable on the far left. This has not been identified, was not originally identified by its eclipse, but through its outburst in CRTS-DR2, I believe. We have an 18th magnitude source in the middle that we recovered, which was discovered in 2011 as the shortest detached main sequence in white dwarf binary. And then lastly, we have a fully eclipsing subdwarf V binary with a brown dwarf companion. And these eclipses are fully eclipsing, so the system parameters were very well constrained. That's another benefit for looking for eclipsing signals. We'll be able, for some of these sources, get good constraints for system parameters, and with spectral's follow-up, be able to characterize these systems and hopefully learn more about the late stages of CV evolution. And then very lastly, we found other systems in our period search of sector 61. I show a couple here, candidate white dwarf plus main sequence stars with periods of 174 minutes and 162 minutes. And this Saturday, I'll be performing spectroscopic follow-up on Magellan, hence why I prioritize sector 61, since it's the first sector that TESS observes with 200-second cadence in the southern hemisphere. But this is just a taste of what is to come. Again, next week, we're going to have more GPUs coming online for a bigger period search. And there's already 5 other TESS sectors in the northern hemisphere we have yet to search, and it has just switched to the southern hemisphere, so a lot more data to come. So with that, I'm going to leave up my summary slide, but I hope I could share some of our excitement about the 200-second full-frame images. And I'm excited to see what kind of eclipsing phenomena we find, especially in the southern hemisphere, where this kind of systematic search hasn't happened before. So thank you, and I'll take any questions.
Just so that we can calibrate, how far away will this be able to identify such objects compared to electromagnetic surveys? Will it give us information about things that we don't see electromagnetic, or vice versa?
Right now, we're not sure how deep we can go yet. I think, like I showed some 18th magnitude stars, the AMCBN was 19th mag, but it'll really depend on how high amplitude the variability is, not just the distance.
So you think that at least that would be useful astrophysically for us to find such systems beyond what we know about?
I think we can find systems that aren't necessarily accreting, like we're finding by eclipses. But as far as farther away, I'm not sure if we'll be able to do that with TESS. Maybe with LSST coming up, though.
Okay, questions? Well, it sounds like everything was very clear, so thank you very much, and we hope to see you again.
Thank you.
Okay, I'm lucky. All right. So, hi everyone. I'm David Gustainov. I'm a Hubble Fellow at the ITC. And today I would like to talk to you about cluster formation, specifically in the Starforge simulations. And I will be mainly focusing on mass segregation. So, since this is just going to be a short summary if you want to know more details, we actually have a paper on the archive, so check it out. It actually has a lot more details that I will be talking about here. So to introduce the problems, so I'm not an observer, I'm a theorist, so my knowledge is very surface level on most things, including star clusters. But what I do know is that stars form in these highly clustered environments, and once star formation ends, which means gas is expelled, star formation is terminated, most of these clusters become unbound and dissolve. However, there are a few who remain bound and are observable. And the other thing that observations seem to tell us is that the way these larger clusters form is basically through mergers. So they are assembled from smaller clusters. So when we try to look at this problem and try to attack it, we actually have several challenges that we need to overcome. And specifically, it's because of the nature of star formation. It has several issues. One is a complicated list of physics involved. The other thing is that the process we are trying to look at, which is starting from a collapsing molecular cloud, then fragmenting, forming subclusters, forming a final cluster, and blowing the gas out, if you actually look at this process, this gas blowout phase is very important in it. However, it's essentially completely driven by massive stars. So when they form, where they form is very important. So if you want to cover this problem, if you want to simulate it, you will need to be able to have a simulation that is the size of this cloud, but also being able to tell where individual stars are. And that's actually a fairly tall order for most simulations. So that's why we are going to be using the Starforge simulations. It's an RMHD code, which involves all these nice physics that are relevant for star formation. But it also does all of these while resolving the formation of individual stars within a GMC-sized cloud. So, okay, let's get started with that. However, the first hurdle that we hit when we try to look at cluster formation in the simulations is realizing what is a cluster. And if you look at intro astronomy textbooks or something, you would find something like it's some kind of isolated, centralized group of stars, but it's not really applicable to the situation we are trying to model here. So let's say, what you have actually looks something more like this when you have an actively star-forming cloud. And it's not isolated, not centralized, it's still actively star-forming, there's a bunch of gas around it. So, you could imagine maybe this is the cluster, maybe it's actually several clusters, maybe it's even more. So we need some kind of definition. And observers, of course, have already run into this issue, and there are several definitions and methods out there in the literature. But in this specific exercise, we actually have a problem that we need to solve that observers didn't have to solve, which is that we have a simulation, which means we have snapshots of different times. We actually have time series data, which means that our cluster assignment needs to be consistent through time. You cannot have something that's a cluster at one time and 2 kilo-years later it's not. I mean, specifically it can happen that there is this issue, but there shouldn't be, in general, there should be a consistent assignment. So I'm not going to go through how we came to this conclusion, but we tried several methods, and in the end, we settled on a fairly simplistic one. So we are using the dbScan clustering algorithm with a characteristic length scale of 1 parsec. It's fairly arbitrary. The conclusions are not going to change if you use a different length scale. However, this algorithm was simple enough and easy enough to clean the final result that we could actually do the analysis. So what happens in these simulations? So on the left side, you can see the surface density map of the gas, and the little dots are going to be stars. The larger the circle, the more massive the star is. And on the right side, you can see what our clustering algorithm says about star clusters, where they are, how they form, what do they do. So in one of these movies, you can see whether your assignment is consistent, for example, because if it was not, you could have, for example, flipping from one cluster to the other and stuff like that. And what you see at the very end, as the cluster dissolves, the algorithm is going to break it aside into smaller and smaller clusters, but eventually it's just going to completely dissolve. So if we look at what happens with these clusters, if we actually look at this movie and try to follow how clusters form, how the final cluster forms in the simulation. So what we find is that initially we have a bunch of small star formation sites which host usually a massive star or maybe a few and several stars around it. It's actively accreting, actively star forming, but also these things are, so because of there's a global collapse, so these things actually are attracted to each other. So you actually end up with these nice merger trees of how these clusters just merge together. And at the end of the simulation, you end up with most of the mass in a single dominant cluster. So these plots here are showing so this is the number of stars, and this is size evolution for this final most massive cluster. So a few things to note. There are all these weird symbols there. It just shows where there is another cluster that this one merges with. And you can see that in the size scale, you can clearly see the jumps. So there was a merger with another cluster, so of course the new one is going to be a bit bigger. In general, we can see that the size scale we prescribe to this problem by selecting dB scan with a 1 parsec length scale biases us towards clusters that are somewhat above 1 parsec. But the fundamental behavior of merger is not going to change. Also note that even though the size scale is biased towards 1 parsec, the half mass radius is much smaller because these things are fairly centralized. So if we look at the stability of this cluster, and specifically its gas content and virial parameter, we can find the following. So first, let's look at gas content. That's going to be this purplish color lined. So initially, the cluster is gas dominated, very strongly gas dominated, essentially like 90-something%. But then gas expulsion happens very quickly. And around the time this happens, the cluster actually becomes unbound. And we can see this in the virial parameter. You might notice that I actually have 3 virial parameters here. So the black one is if you just take the simulation and say, OK, let's calculate the virial parameter. And if you do that, you find that, oh, this should be bound, and it should be even more bound as you go ahead, which, of course, is obviously wrong because you can see it with your eyes. That's not what's happening. I'm basically including this as a warning to people who use simulations to be careful with this. So this is wrong because this is a result of a finite resolution effect. Essentially, what's happening is that if you have binaries that are very close to each other, your gravitational softening will basically make their motion not correct, not physical. And what you end up with is that you end up with an excess of potential energy. So you can easily correct that by just merging these binaries and multiples into a single system. So you make like a system virial parameter. That would be the green one. But if you just took that into account for the stars, you would see that we should be always unbound. Of course, there is a bunch of gas. So if you account for the gas as well, that would be the red one. Then you can see what's happening, that you have a virial parameter below 2. But once gas expulsion happens, it goes up. And then, of course, it can go down as you break apart your cluster into smaller and smaller parts. Since we are talking about clusters breaking apart, so stars are not going to necessarily remain in a cluster for a long time. And as the cluster grows, it actually ejects stars. So one of the questions we were interested in, how is the stellar population that's not in clusters or the stellar population that is ejected different from the one that's in clusters? Is there a preference to eject, let's say, less massive or more massive stars, for example? And so these histograms basically compare these populations with the total stellar population. And what we finally find is that within our uncertainties, we find that there is no preference. It seems that the stellar population, at least in the simulation, which are ejected or have basically follow the same kind of IMF as the ones that remain. Oh, okay. Really? Oh, okay. Okay, I'm going to just go very fast here. I'm sorry. So the last part we looked at is mass segregation. So stars observed to be in clusters, they are also to be mass segregated. That means that massive stars are at the center, less massive stars are further apart. And there's a big question. Is this primordial? Is this just how stars are born? Or is this somehow a result of some kind of interaction? Is it nature versus nurture? And I'm just going to skip that. So we can define various metrics for mass segregation. And bottom line is, what you're going to find is that whether mass segregation is primordial or not essentially depends on how you quantify it. And the two versions I use essentially give different results at the start. So the red one says that actually mass segregation is non-primordial, but the black one says they are. By the way, if you're interested, so the two things, so the one that says it's not primordial is based on minimum spanning trees, and the other one is basically based on like taking an offset from the center of the cluster. So the key insight from our mass segregation study is that to answer this question, is there primordial mass segregation, you have to provide two things. A, what do you call a cluster? And B, what do you mean by mass segregation? If you provide both definitions, you can get fairly different answers. Essentially, if your definition of cluster allows it to have substructure, then, for example, if you use a metric which would assume that massive stars at the center in a mass segregated case, that's what the minimum spanning tree does, then you would actually say it's not primordial. But if you say, oh, I'm just curious if it's distributed differently, then you would find that it is primordial. Okay, I'm sorry for going over time. If you have any questions, please let me know.
Thank you, David. Some people think that the solar system was born in a cluster and that had some impact on the solar system. Do your simulations help in any way understanding what the impact was? And could the sun have, for example, a companion that was lost as a result of the ejection?
Yeah, I mean, technically, so our simulations are run until gas expulsion, but actually we are working with others who are continue to running it with n-body simulations. So just from this simulation, if you pick a star, like a solar type star, you could follow its evolution and say, as it formed, what kind of, radiation background it had, how many companions it had. So yeah, we could say a few things about it. The big uncertainty is I have no idea what the cloud or cluster was where the solar system formed. So there could be a large variety of initial conditions there.
Right. Charles?
So I've got a question about the late stages of cluster evolution. The significant fraction of field stars are in binaries, and models based just on the ejection from clusters do not fail to produce a large proportion of binaries. And the suggestion has been made that they're sort of laid in the process that you're describing here. Do you see any evidence for that, or is that something that you can follow up on?
Sorry, I'm not sure I caught the question correctly.
Do you find any evidence, or could you find evidence that binary stars are selectively produced during this process?
Okay,
Because
so
we see preponderance of binary stars later on.
yeah, so in this, the simulation produces a lot of multiples and binary stars. These are long-lived, so they survive the dissolution of the cluster. We haven't looked at whether the binary properties of stars within the cluster and outside the cluster are different or evolve differently, but we could.
There are no more questions. Oh. There is a question behind me. Please.
Thank you, David. So this is a simulation of one forming cluster. But as we know, these clusters actually move through the interstellar medium, and as my friend Joao Alves likes to say now, they experience galactic weather. So they, come upon other clouds that some of their previous feedback episode caused and everything. So basically, do you think that moving this cluster through other high density or low density regions would affect your results?
I think yes. For example, I could imagine that if you have two clouds colliding and you create a high enough surface density environment, you could have a high enough star formation efficiency that you end up with a bound cloud, bound cluster, which would naturally evolve differently. So I mainly showed results here for one single simulation here. We did not run one simulation only. We ran several with different initial conditions. And we are actually, it's not in the paper, but we are actually right now experimenting with cloud collisions. It's not specifically necessarily that completely the galactic weather that you described, but it's related to that. And overall, we have this future plan where we want to integrate Starforge runs within a Fire Galaxy run, so then you would have a somewhat self-consistent galactic environment there.
Let's thank David again.
I like the grad
Oh,
and
yeah.
all the work, so.
Right. Yeah, so I'm going to talk about a recent project that we just put out on the archive a few weeks ago. So it's a collaboration between a mathematician friend of mine, and basically it started with there must be some way we can find something we could work on and publish a paper on. And so then eventually we realized we weren't going to get it done unless we could find a grad student to do all the work. So it's topology. So I'm not exactly an expert on topology, but this guy is, so that's good. So I'm going to talk about some surprising things that we found. So, all right. So here was the motivation, like why would we use topology? And so we even saw some of it in the talk we just saw. So this is from the Illustrious collaboration, so this is much larger scales, but there's a long history of people trying to find this cosmic web, right? Tracing out filaments and the voids and then the intersections. And that's obviously something about topology. That's something to do with connecting components and holes and shells and things like that. So there's a long history of people searching for the signature of topology. And that's in the dark matter. So people have tried to learn about cosmic structure formation that way. But I, look at so this is to say the gas metallicity or the temperature. And if you look at those movies from the Illustrious simulation, you see these AGN going off, and you see these huge holes get blown everywhere, and you're like, oh, that's a hole, that's topology. And you can see in the gas temperature, you see these giant gaping holes all over the place, and galaxies get formed out of, hot gas that cools down, and cooling rates depend on metallicity. So the motivation was, well, maybe we can actually see the signature of some of the metallicity or temperature topology in some property of the galaxies. So what I'm going to tell you is that we haven't done that yet. So that's not what we found, but this was a motivation. And so we're just kind of on our way down this path where we found something that was more sort of kick you in the face obvious first. So I'm going to tell you about the kick you in the face obvious part. And someday we might be able to do it this way. All right, so just as a warm-up, so topology of galaxy catalogs. So the first thing is galaxies are a point set. And so with just a bunch of points, we need some way to actually somehow build this up into some network. And so there's a whole machinery that goes along with this. So the way we did it is we basically said, so we did these things called an alpha complex, which is to say, you first of all connect all these things using Delaunay triangulation, and then you just grow little spheres. And then you connect the vertices if they're within some distance of each other, and then you just grow things as a function of that sort of linking length. So this thing alpha is a linking length, and you can see that you link these things together, and as you grow that linking length from the points to 1 megaparsec, 2 megaparsecs. Eventually, you start to connect together this network. And as you connect together this network, what you see is you start to see these holes coming out. And so this is in 2D. It's just easier to visualize it in 2D. So we did this in 3D. So in 3D, you can do things. You can count the number of independent components. So in this case, every galaxy here was an individual component. Here you see the number of components has gone down. So the number of components, and then in 2D, there's the number of holes between the components like this, which is the number of loops when we do this in 3D. And then the third thing is the number of shells. And so if you just count the components, the thing to use, these are called the Betty numbers. So the Betty numbers is the number of standalone objects. The number of loops you can draw is beta 1. The number of shells is beta 2. So a torus is one object, and then there are 2 different loops you can draw in there, and then there's 1 shell around the outside of it. A sphere has you can't do any little loops in a sphere, so it has 0 of these ones. So these are the Betty numbers. And you can see that as you vary the smoothing length, you're going to change the number of the Betty number. So this is the Betty number as a function of smoothing length. So the number of components drops as you start to link things together, and then you start to grow some number of holes. So you see we're growing. We start with no loops in here at all because everything's just connected. And then suddenly you start to have a few little loops in here. And then eventually, once your whole space is connected, you're back down to 0 loops. So it goes down to there. So 3D is the same thing with shells. So the first thing you see here is that there's kind of a characteristic peak here. And then you would say, well, what's that peak coming from? And so some people, so then we backed off and we said, what if we just do this for random points? Because you can imagine doing all sorts of constellations in here. So what if you just do this for just a pure Poisson sample? So if you just do random points and you do these same Betty curves where you just grow the smoothing, then what you see is you see large variations just based on the number density of points. So as I vary the number density of the points, there's always this characteristic peak that emerges. So so this is increasing the mean spacing this way, and there's just basically a big peak at whatever scale corresponds to the number density of points. And that's just so there's a scale that's going to come out of this. It's just, if you have a point set and everything's kind of this far apart on average, you're going to get a signature on that scale. And that's just coming from just the randomness of points. And then if you scale out by the number density, as you'd expect, you get some scale invariant spectrum. Okay. So we did this with dark matter halos, first of all. So we went into some simulations. You extract the dark matter halos. You do the same thing. And the first thing you find is that you see that as a function of the scaling, so this is for different mass ranges of halos. So these are the low mass halos. So there's a lot more of these. These are the high mass halos. So as you vary the number of halos, you just see this characteristic scale in the Betty numbers just walk out towards larger smoothing just because they're rarer. If you take out the number density effect, what you find is that, again, the dark matter halos kind of clump up to give you a fairly scale invariant spectrum. So mainly what looks like the topology of the dark matter halos is mainly we're just measuring the number density this way. And you can see there's these small variations here. And this is the stuff when people say they're looking for stuff in the cosmic web. Anyone using the Betty numbers is using these small variations after scaling out the number density to say something about the way dark matter halos are populating the cosmic web. So the shells versus the loops versus the connected components. Okay, and so this kind of validated us that, you know what, maybe this is good because if the dark matter doesn't have any interesting topology on its own, then everything left is coming from those bubbles getting blown by the illustrious simulation. So then we said, let's do the same thing for galaxies. So you go in, so we did this with the TNG 300, and then we also did this with the camel sets. And we just said, what are these curves? These are called the Betty curves. So as a function of this scaled smoothing length. And you see something's different. So this is the level, so you see there's this kind of a curve that goes up and comes down. And now something's different. We have curves that go up and come down and go up again. So what's going on? So there's a second length scale that's imprinted in the galaxies that's not there in the dark matter halos. So in the simulated galaxies. And so if you just do it by all galaxies, that's the blue. So blue's got kind of a smaller bump. And so let's just look at the shells because I can point to it. So these are just all galaxies, but if we split them by their star formation rate, which is to say the ones above some star forming rate, the ones below some star forming rate. So the star forming galaxies actually look a heck of a lot just like the dark matter halos. You just see this curve goes up and comes down. Whereas the quiescent galaxies show this second peak. So it's something about galaxies that are not actively forming stars are showing this second characteristic scale. So what's interesting is that it's not the same for different ways of modeling galaxy formation. So if we look at, say, the CAML semi-analytic models versus the TNG sims, that's dashed versus solid. And you see the peak's not quite the same, even though this scaled peak, the one based on number density, is basically the same. So there's something about the way these models are forming quiescent galaxies that's giving you some small difference in what this peak is. All right. So what we thought was going on was that, okay, well, so quiescent galaxies tend to live in galaxy clusters. So galaxy clusters have long been known to have this problem of if you just don't do any feedback at all, the galaxy cluster just forms one just humongous galaxy at the center. And so it's known that you had to put in some feedback. And the typical feedback that gets put in is AGN feedback, which is exactly those bubbles that were being blown by in the movies of these illustrious simulations. So in these semi-analytic models, they actually have these huge suites where they did these dark matter only simulations and then dressed them with galaxies and then put in recipes for how to form galaxies, and you stir it around and you can do different combinations. Oh, so this is perfect. And what we found is that if you look at all of the models in these CAML semi-analytic simulations of galaxy formation, that if you do the maximum AGN feedback, like the hugest bubbles you could blow versus the little tiny bubbles, these curves look almost identical. So basically, AGN feedback has nothing to do with any of these variations. Instead, the only way to get variations in this other bump is actually by playing around with the supernova parameters. So there's something about the way these galaxy formation models are implementing supernova formation that's changing what's going on in the cores of these galaxy clusters on scales of about 200 kiloparsecs. So we're just getting started on this. We haven't quite figured out where to go with this, but the topology is different. We found this second peak, and it's something to do with, so it's about 200 kiloparsecs, and it's non-star forming galaxies, so it's basically galaxy clusters. You can go poke around, and you'll see that it seems like it's galaxy clusters. And I'm not sure this is the best way to have found this. So what we think has happened is that we've found something using topology, but there's probably a better way to find it. So if someone has an idea of how to do it, let me know. That's it.
So Gil, there is definitely the number density peak that you talked about.
Yeah.
Could it be that we're talking about sub-halos that introduce another scale, which is the viral radius of the halo they reside in?
Yeah, so you can break it into centrals and satellites, and you see that the centrals versus satellite, it doesn't quite give you a second peak, but it kind of gives you like a hunch, like a little bit of a lump if you break it into centrals versus satellite. But I think it's the extra step of centrals versus satellites plus quenching in the clusters is the extra thing that has to happen, is what it seems like it's doing.
Last question, go ahead.
I had pretty much the same question.
Oh, was it the same question? Okay.
Yeah.
Let's thank Gil and all the other